and action. All right. Let's see here. Just a little bit of review from last day. It's just on Friday, but feels like a lifetime ago. We talked about composition of functions. So we can put a function into a function and get a new function. And so we talked about function composition. And as long as you are careful and just kind of work methodically, they're not that bad, right? Let's see what we did. I want to use this one for a reason. Let's think about this one again, but we already solved it. And womp womp, we found that the two compositions end up being the same. That's not always going to be the case. Or that's usually not the case, I should say. Oh, that's not what I wanted. Hey, I grabbed it. Fine. As a little bit of review, we'll just do this one again, or one of these. So we're just gonna do this one because they end up being the same. So the same kind of rules apply, right? We've already done it. So from last day, we're gonna do this one. But what I want to talk about is throw in something that we didn't talk about on Friday, was the domain when we have composed the function, right? So what's important is that, okay, so I'm putting g of p into f of p, right? So that's fine. But now the key thing with finding the domain, remember the domain is the list of all the possible inputs that I can put in. Well, one of those concerns is that, well, g of p has to be defined if I'm going to put it into f of p, okay? And so to find this is new, but the domain of, can I say composed functions? I don't see why not. Function composition. Feels weird, but composed functions, right, need to account for the domain of the function that's going into kind of the inside function, let's call it, as well as the final function. Okay. So the domain of composed functions need to account for the domain of the inside function as well as the domain did I record? And let's try to not be on mute. Okay, phew. As well as the domain of the final function. So if we have here, if we want to find f of g of p, okay, let's do that. F of g of p, what we're saying is that g of p, we need to find the domain of g of p, right? It has to be defined before you can put it into another function, right? Since it must be defined. There. G of P was 1 over P. One over P, and f of P was what? The root of P? As a general recap, right? What were the two rules that we're gonna have a stronghold on? I can't divide by 0, right? Any value that makes me divide by 0 has to be removed from the domain, right? So here, number 1, can't divide by 0. Therefore, P cannot be 0. Just in general, right? We had a rule for square roots, which is why I wanted to go back to this one, right? Because it covers both of the main players. I can't take the square root of a negative number, right? And so we can't take technically the even root, but we'll focus on the square root. Can't take the square root of a negative number. Which means in this case, therefore, P, if f was the inside function, then P must be, wait, I don't know what happened there, but that's all right. Must be greater than or equal to 0. I'm realizing that sometimes I do what it can't be, and sometimes I say what it should be. That's inconsistent. But what am I doing? I'm just cutting corners, right? What's the easiest thing to communicate? Well, P can't be 0, it means it can be everything else, right? Or the restriction on P. Both of these work, right? If you wanted to write this one as, okay, P can be in the set of real numbers where P is not equal to 0, that's fine. But I'm just being lazy, I think. And it's what comes naturally, so can't be the first time I'm doing it. All right, so what did we do when we found f of g of p? F of g of p says, okay, take g of p and use it as the input into f. Okay. So then I have the square root of 1 over p. To find the domain here, what do I have to remember? I have to remember, okay, well, that's still true. P can't be 0, even if we have it written like this. Okay. But then under the square root, what we're saying is that 1 over P, or if I want to rewrite it, maybe we'll leave it like this because I don't want to get too deep into it. So then 1 over P has to be greater than or equal to 0. Let's do the inside function first, right? From g of p, p cannot be 0. It's fine. From f of g of p, 1 over p has to be greater than or equal to 0. Now you do a mashup of these, okay? Which means that, okay, 1 over P has to be positive. How can I force that? I can force that by making P positive, right? The only way that I can get 1 over P to be negative is if P is negative, right? And so here, force this to be we force P to be greater than or equal to 0. But then we've got this additional, which means that it can't be equal to 0. So now we're just forcing it to be greater than 0. Right? These are tricky, I think. But we're not going to do a lot of them. So don't worry. Unless you go into calculus, then you'll do more. But now you've seen it. There were some on the assignment though, so that's why I wanted to bring it up, which I think I've posted already. 1.4. Did I? How am I supposed to know? Well, Emily, aren't you manning that thing? Yeah, I am. In theory. In theory. Right, so therefore, the domain of f of g of p is p greater than 0 in this case. Nice. Because sometimes when we've done the composition, we can't see the original conditions anymore on the inside function. So that's why you have to look at it first, the inside function, find that domain, and then find the overall domain and only take the overlap. Nice. That wasn't review, but I'll call it the end of the review. How cheeky is that? Cheeky, cheeky. Section 1.5 is on transformation of functions. So like I was saying, when we introduced those toolkit functions, right, knowing what x squared looks like, right, it's parabola like this, then we can manipulate it or transform it into some version of a parabola, right? I can squeeze it together, or I can expand it a little bit, or I can shift it to the left, I can shift it to the right, I can shift it up, I can shift it down, I can flip it. I feel like that's a dance move. Whoa, I can tilt it, I can do all these things, right? And so knowing what the core function looks like is going to let us transform the function, and that's how we generate all functions, right? Now, I will say this, there are a lot of things that I'm just going to copy and paste from here. And what I want to do is just generate a sheet, kind of a cheat sheet of transformations that you'll have. I don't like testing this stuff so much because it is just memorizing how different things impact the function. And I don't think that there's real value in that, right? So it's more of an assignment type question where you have time and you can work through it and you can talk to your friends and you can kind of, you know, approach it with calm, because sometimes it takes a little bit of work. So if it feels like I'm rushing through it, I kind of am, because in terms of kind of testing this concept, I'm not going to. It is something we have to talk about. So here we go. So it's going to be a lot of these boxes which will make up, got confused about what we did today. What the? Where's the note? Oh, there it is. Scrolling, it's hard sometimes. There. So maybe what I'll do at the end of today is just take all these boxes and put them in a separate sheet and post them on Moodle so that you have the cheat sheet, because obviously I'm going to write a little bit around these. Okay, but it's not something that I expect you to memorize. Just know that it exists and you can do it given enough time. So if you have a function f of x, right, if we define a new function g of x, which is f of x plus k, where k is some constant, so we're going to use k as a constant just throughout, okay, then what are we doing? We're taking the output and adding k, moving it up, right? I take all my outputs and I increase them by k amount, right? That's moving things up. Okay. So here, if I have g of x is equal to f of x plus k, what's that saying? It says each output, which is f of x, maybe I'll say to each output add k. We've got the added condition, right? What's subtraction? Subtraction is just a special case of addition, right? You can derive subtraction by saying what? Well, it's just adding a negative number, right? And so that's subtraction. And so you don't really need to outline both of these, but it's nice to be clear. So if k is positive, right? If it's positive, if I'm adding a constant, then the graph is going to shift up. And if k is negative, then I have to shift my outputs down, right? So depending on if you've got f of x plus k or something that looks like f of x minus k, right? If it's subtracting, then it's going to shift it down. I think that one's pretty good, right? Seems reasonable. Right? Where is it? Oh. What about horizontal shifts? What's the difference between the one we saw before, f of x plus k, and f of x plus k? If you say it, there's no difference, right? Or it's very subtle. But now notice that k is being added to the x. Okay. Now, what kind of gets me is if I do x plus k, so if k is positive, then the graph is going to shift to the left. What's my left? This way. To me, that's backwards, right? That's how I had to memorize it. Oh, I do it backwards to what I want to do, right? But like I said, it's part of the reason I don't want to ask you to memorize it. I don't think there are other things that you're going to be forced to memorize. And so I'll save some memory space. So here, if you have g of x, oops, I like to be somewhat consistent with my colors. If g of x is f of x plus k, right, notice the plus k is on the x, which is the input. then, for example, if you have k is positive, then it shifts it to the left. And if k is negative, right, so x minus k essentially, then it shifts it to the right. That's weird, right? I think. I'm also trying to not talk your ear off. Just get to the point. Let's do an example where we have x squared, just so we can see how it behaves. Okay, x squared, like I said, it's our go-to function. It's a little bit more advanced, but not too advanced, right? So that's why it's nice to look at x squared. So if you're in Desmos, x squared looks like this. So now I can do things like x squared. Well, let's talk about plus 2. That does what we expected it to do, right? I take my function, the x squared, and then I add 2, or if you want, you can subtract 2 or some version of that, right? That was the vertical shift. I had to think horizon, anyways, it's hard. What if I have x plus 2 squared? So when I add 2, it shifts it to the left. If I do, and I should specify, if I subtract 2 from x squared, shifts it to the right. Now to clean this up a little bit, I'm going to delete this blue one. Right, there are different colors, which might be hard to see, but I'm going to delete this blue one because I think that one's under control. It's the horizontal shifts that I want you to see. But kind of fun. Can play around with Desmos a little bit. So I'm going to screenshot this. Done. My camera roll on my iPad has got to be kind of the most boring camera roll anyone's ever seen. I don't want you to. No. No. That's why I'm kind of, we're touching on the subject just enough to satisfy the powers that be. Right, and so here the green one maps to the green one, the purple one maps to the purple one, right? Yeah, something went wrong. Yeah, this is when it would pay off to be on mute, I guess. That's when we have to go back. Oh yeah, we will find, we'll find minimums and stuff, but later. I know. Not for this. Today, we're just talking about shifting graphs and manipulating graphs. Yeah. And the reason there's lots of reasons, but the main reason I didn't cut it completely is because you need to know that it exists and that it's possible, right? And that's how functions behave. But besides that, reflections. What's another thing we can do? Well. Oh, weird. There. I have a function f of x, then if I take that function and multiply it by -1, what does that do? It takes all my output, my original outputs, let's think about x squared, and makes them negative, right? And so this is going to be a reflection about the x-axis, right? So here, if I have g of x is negative f of x, this takes the original output, so I guess, and makes them negative. Which is going to look something like, if we're talking about x squared, right? If f of x is x squared, then g of x negative x squared. And I should be careful here. Negative x squared in brackets. Also works if you have something like x to the power of 3. What does x to the power of 3 look like? X to the power of 3 looks, that's a terrible x to the power of 3. But now it would take all my negative values and multiply them by a negative, which means that they're now positive. A negative times a negative makes a positive, right? It takes all the positive values and makes them negative, right? So again, it's a reflection around the x-axis. I think we're better off maybe turning to Desmos here. Delete these. What if I have negative x squared? Okay, phew. What if I have x to the power of 3? Just focus on this one. Will it do what I just said it would do? Does. Phew. Right, and so it just takes your outputs and makes them negative, but that depends on if the output was positive or negative for the results. And hopefully that's clear in terms of the colors. All right. So that's when the negative is on the output, so on f of x. What if I put the negative on the x instead? Then all my x's are negated. So now this is a flip around the y-axis instead. And so here, if g of x is f of negative x, each x is negated, which looks like what? Let's see here. Let's do, sure, let's use x to the power of 3, negative x. Right now I want to put it on, oh, which looks the same. Oh, I know what happened. I did do the same thing. Doesn't like that. X bracket to the power of 3. Okay, I think I know why it's not behaving. It is behaving because it looks the same. Let's do x to the power of 3. Or is that going to work? It's going to be hard to see because all of these are symmetric. That's one. How about just x and negative x? Well, that's the same as well. We need bigger functions to be able to see it, but I don't want to do that quite yet. Right? They look the same for now. They're not, but they look the same. We need bigger functions. Bless. What were we seeing? We were seeing even functions because the output, f of x, right, is going to be the same as f of negative x. And so an even function, you put in a negative x, and if you're able to simplify it down to just the original f of x, then you have an even function. And so the graph of an even function is symmetric about the vertical axis, which is the up and down one. Okay. X squared, for example. Hey, why didn't it work? Oh, because it flipped. Anyways, we can have odd functions. How do we test it? Well, if I put in negative f of x, do I get the negative f of negative x, which is really the same as negative f of x? Okay, so how you test if you have an odd or an even function is you can put in negative x and see if you get f of x or if you get negative f of x. So to see if a function is even or odd, we use negative x as the input and simplify. If the result is f of x, so back to the original function, right, then it is even. And if the result is negative f of x, then it is odd. Ugh. We've got some examples. I feel like we did these, but sure. I got carried away, I guess. Wait. I encourage you to get used to using Desmos for these, right? You can put in, so make a table of x values and then make a table so you can make values like -2, -1, 0, -1, -2. and then make a new column of x plus 2, right? And so -2 plus 2 puts me at 0. -1 plus 2 puts me at 1, right? 0 plus 2 puts me at 2. See how all the outputs are just being shifted, whoops, up? No, it's on the x. Use Desmos. I wanted, what did I want here? Can I do this? Snazzy. Oh, you can't see it. Hey, I'm doing this really cool split screen thing, but it's not showing up. It's weird. Can't marvel at my tech savviness. All right, so let me just, okay, so it's keeping it on here. What if I change it to here? It's not working. All right, then I have x, oops, not double bracket, x plus 2, I'm putting it into Desmos, and then squared. Oh, because I squared it. Okay, let me just, you can't see it, but I'm punching them into Desmos. Curious to know how it shows up in the recording. If it shows this screen or my actual screen. Don't know. X squared and then -3. And then, oops. X -3 squared and then +1. Mostly because I needed to see what these were all about. Red one shows the shift to the left. Probably the square that's messing me up. Anyways, screenshot. Who knows? Maybe the reason I don't make you do these is because I don't like them. Oh. Wonder if I can just have them like that. Sure. Just do it in Desmos. It's not something that you should be doing in, oh, in Excel? Oh. No. Just know that you can do it. It can be done. But no. Like I said, in terms of memory space, it's not worth it. Right? You're better off just having the cheat sheet and then you can pick your way through. So on an assignment, yes, because then you've got time, right? You come for help, all that kind of fun stuff. But on a test, no. Okay. We already did this, but how about this mumba jumba? I'll do the other ones as well, just on the same graph, but this one, right, what's it doing? It's going to shift it to, so how am I going to start this when I'm reading this? I'm going to start just like any function. I'm going to start inside and then bloom out, right? So inside the bracket. So first, x minus 2 is that backwards one because it's on the x. So it's going to shift to the right. I'm looking for guidance here. Right, so that's the backwards one to me. I don't know. Okay, so shift it to shift right 2. I'm gonna go up 2. I'm avoiding the 1/2 because we haven't talked about squeezing it or that yet. I think I jumped in too fast here. Up 2. We can do the negative. The negative of the outputs is going to be a shift or a transformation around the x-axis, right? So here, flip on the x-axis. So far, you can kind of map these out, but here's the pickle that we haven't seen yet until now. I hope. Stretches and compressions. So if g of x is k times f of x, where k is some constant, that's what we saw, right? We saw k is 1/2. Then it's either going to be a stretch or a compression. So a stretch or a compression of the function. So if k is greater than 1, right? So, well, greater than 1, I don't know how else to say it. Not a decimal, right? Then the graph is going to be stretched, but that's not what we had, right? We had k is 1/2, so 0.5, right? So it's some decimal between 0 and 1, then it's going to be compressed. Okay? And if k is less than 0, which technically we have, right? We know how this negative behaves, but then it's going to be a combination of a stretch or a compression with that vertical reflection. Yeah. So if I have to graph this, remembering that f of x is x squared, okay, first thing I want to do is just take this and negative 1/2 f of x minus 2 plus 2, right? Where f of x is x squared. So what I want to do is I want to rewrite this without that function notation, right? Because f of x is x squared. So here, f of x is x squared. So this becomes negative 1/2, and then f of x is x squared, but I want to replace the x with x minus 2. So then I get x minus 2 squared. And then plus 2. Right? That's what I have to do to be able to graph it in Desmos. That's not even just graphing it by hand, right? That's so that I know what to put into Desmos, and I forgot a negative. No strike for me because I caught it first. Although I feel like I'm a couple strikes in, maybe. Monday morning and all. All right. So let's plug this into Desmos and see what happens. What did I have? I had negative 1/2. Now, when you're entering, Notice how the cursor is still on the 2, so then you'll need to step it up. Otherwise, you're building your f of x in the denominator, and that's not what you want. So just make sure it's really good about doing what you told it to do, right? But you need to be careful what you tell it to do. So then a bracket, and we had x minus 2 or plus 2? Plus 2 squared. Okay. And then now I've forgotten it all. Oh, minus 2 and then plus 2. That's all right. Minus 2 squared, step it out, plus 2. Okay. From the original, which was just x squared.
Wasn't it supposed to be a compression though? Or it's one
Yeah.
Or no, it's -1.
But the negative is the flip. Yeah, why is it looking?
Anything less than 1 is going to expand it out, and 1 is going to make it.
But
You put 0.5 instead of 1/2, would that make a difference?
let's see. No. What if? It still looks wider. But it says, right? I'm not crazy.
Well, it's the only reason I said it.
Huh.
5 2.
I guess my qualm is either I don't know what stretched and compressed mean. Whoa. I would have thought this was stretched, but what if we're stretching like this and compressing like this? Oh, that's weird. That's weird. It's another counterintuitive thing. Yeah, but it's so when it says compressing, let's see here. Maybe I need to have a paradigm shift. A stretch is stretching this way. Okay. He wouldn't have a typo. He's the king of pre-calc. I don't know if that's true, actually. Yeah, I mean, the more I think about it, it makes sense. But now I want to have the compression. That doesn't help, does it? I want to have it going this way, which means it's going and getting flatter. This just turned into a little guy, but this is what it means. Okay, I knew there was a lot of counterintuitive stuff in here. I thought, I've got it. Okay, so now Desmo's not lying, isn't lying. David Lippman's not lying. Let the record show. And just to match what we wrote, I am going to keep it as 1/2 there. Screenshot that, bring it in. Oh. So here, this gets smushed down. Compression makes it wider. We should call it smushed. Is that how you spell smushed? Is it even a word? I wonder if it is a word. It's smushed. Smushed. All right. Tricky, tricky, tricky. Otherwise, we had it going on, right? We shifted it to the right. So we take this, and what's kind of fun is I can draw this, oops, sort of, and I can move it. So we shifted it over 2, and then we had to smush it. Now, how am I going to do that? There. And then I had to flip it. Oops. I guess we flip it first, maybe, and then put it down. That's a terrible drawing, but you get the idea, hopefully. And if you don't, just put it out of your mind. More stretches and compression. Hey, it's not letting me copy it. Copy. And compressions, but in the other direction, horizontally. So if you have the K, so now it's multiplying on the X, right? Instead of the outside function, it's on the inside, the input. Okay. G of X is F of K times X. Notice it's multiplying the X. Where K is some constant. If K is greater than 1, then, oh boy, then the graph is going to be compressed by 1 over K. So if K is greater than 1, let's pick a value 2, right? Then it's going to be compressed by 1/2. Okay. If K is between 0 and 1, such as 1/2, right? Then the graph is going to be stretched by 1 over 1/2, right? Which is really, it's going to be stretched by 2, right? 1 over 1/2. Can't remember if we've reviewed fractions. Fraction over a fraction, you have to flip the denominator and multiply. And so, right, if K is greater than, oops, 1, say K is equal to 2, then it's compressed by 1 over 2. That one's fine. The one I wanted to focus on was if K is between 0 and 1, say K is 1/2, then it's going to be stretched by 1 over 1/2, 1 I can write as a fraction as 1/1 divided by 1/2, only because I've got a page break here. 1/1 divided by 1/2. Kind of unfair because we haven't reviewed working with fractions yet. But flip and kiss, if you remember that, right? You take your denominator and you flip it and then you multiply, kiss them. Here's a kiss. 2/1, right? Multiplying fractions, I can just multiply across. 2 times 1 is 2 and 1 times 1 is 1, but 2/1, anything over 1 is just itself. So 2. So it's stretched by 2. If k is less than 0, right, so now it's negative, then you're going to have a reflection in there as well. I like to think of the reflection as kind of its own thing, but let's see what the examples have to offer. Kind of going rogue here. Question is, do I want to do this one? Okay, not yet, sorry. Maybe not ever. Because it's one of those where we have to draw it, and I don't like doing that. I should say I don't like making you do that. Let's do another function. So for example, I'll pick a different one. This one here. Let f of x be, usually I use x squared, obviously, but how about we do, should we do the root of x? Root of beta. Sticking to those toolkit functions, right, that we know what they look like. What does the root of x look like? We'll start there. Oh, not Zoom. Desmos. So let's start by mapping out the root of x. Okay. Phew, looks like what we expected, right? The domain for the root of x is just x greater than or equal to 0, right? But now I can manipulate this thing. And what if I want to do, I'll steal this. We'll do this. I'll delete that. I'll write it out as if I came up with it on our own. Use Desmos to sketch a new function called g of x, which is 2 times f of 1/2 times x minus 1. Notice that that 1/2 is on the x, right, and not the y, and then we have a 2 on the y. That makes sense, maybe. Then I'm gonna do that. Okay. So again, the step that I have to do between here and Desmos is I have to take this function f of x and I have to use it in here, right? And apply this transformation to the root of x. So, okay. Everything inside the function, right, is going to go in the square root. Okay. So here, this is the input. So I get 2 times the root of 1/2 times x minus 1. Close the root there. Wherever you see an x in the function, you're going to replace it with 1/2 times x minus 1. Okay, we did that. And then we're going to multiply that by 2. We did that. And the only thing that's left is plus 3. What are we doing? We're just doing compositions of functions, right? I have this function, 1/2 times x minus 1. I'm putting it into f. And then this is technically another composition, right? I'm just throwing functions into other functions. Okay. All right. How about this? On a test, this is what I'll ask you to do, right? What would you have to enter into Desmos? That's reasonable. That's a good skill to have. How about this? Test question, right? None of this actually mapping it. That's nonsense. Given a function, f of x, and the transformation, this is more a note to myself. Pretty good question. G of x. Find the function you would need to enter into Desmos. If you can do that, you've done the transformation. I think that's pretty reasonable, right? Okay, so starting on the inside, I've got moving nice and slow. I've got 2 times, I don't know if I need to have the multiplier. Let's see. 2 times the root of, now I've lost it. 1/2 times x minus 1 inside the brackets. 1/2, step it up, bracket x minus 1. Notice how it's not in the square root, so I want it all in the square root. So I have to fix that. Times there, x minus 1, bracket 1/2 x minus 1, and then plus 3 outside the square root. Woo. The stretches and compressions aren't obvious to me here. What if I zoom out? Is it going to help? Probably not. It's like a little bit more open. But when I zoom in close, at least the horizontal shift and the vertical shift, they're obvious, right? I have to move to the right, right? X minus 1, I have to move 1 to the right. And then overall plus 3, I have to move it up 3. And then the stretches and compressions, well, it's anyone's game. That's not true. But for us, it is. Nice. Okay. Don't really want to start a new section. Are you okay to end early? Sorry. I know.
It's all right.
Can I ask a question?
Yes, yeah. Do you want it here in class? Does anyone have any questions? There, I ended just kind of like, there, that was terrible, wasn't it? But now it's over. We're on the other side. We multiplied it by -1, but it was a negative function and we multiplied it by -1, so now it's positive. If you have any questions, let me know. Otherwise, I'll see you on Wednesday for inverse functions, which are way more fun. I'll end this.